Yeah, thanks a lot, Malte, for this very nice presentation, and thanks a lot for inviting me, you and Bruker, for giving me the possibility to talk about the work that we've done, and of course, partially that was done with instruments we got thanks to you guys. As you can see here, like I will talk today, of course, about parts of our work that is mostly related to 3D situation, 3D tissue flow. And before I forget it, I would like to start with the heroes of this story, which is first Shweta Raghuraman, who is the person who was studying cancer cell spheroids, and that's what you can see here already. We will talk about this in the first part of the presentation. And then there's Bernhard Wallmeiler and Alejandro Llorado, who are two PhD students. Bernhard already finished, and Alejandro is in the work, who are working on zebrafish. And that will be the second part of the presentation. I would like to directly really dive in immediately into the question of what Shweta was doing at the time when we studied cancers or cancer cell migration. And I have to see if this starts working. Yes, okay, good. And we were really interested in understanding tumors from a biophysical perspective. And as you might know, is a tumor, when it starts off, it's basically a ball of cells, as you can see here. And typically that's embedded in an extracellular matrix that's surrounding it. And nowadays, tumors themselves are not a big problem anymore in most situations, but what really comes to a problem is when the cell-cell interaction between these cells, that's typically mediated by biocaterin, starts to like get loosened, and then these cells start to migrate out of this primary tumor and they start invading the tissue. So the question that we're asking here is, or what a lot of researchers and colleagues are actually asking here, is to which extent we can understand better what happens there when cells start moving out of such a primary tumor. And what is actually not a lot appreciated in the field are questions related to pressure, what's going on inside the cell. And what we know of is that we have here at the inside of such a tumor some certain pressure and forces that are kind of like pointing inwards, but we also have forces acting with the environment. And what do we know, right? We know that we have quite some variable pressures inside, but the question of how pressures are related to driving the tissue is not very well studied. They will, of course, also exert pressure on their surrounding, and we kind of also know that changes in the morphology, right, of such a tumor spheroid may also be based on ECM rigidity. For example, it's known that the stiffness of the environment is very important for outgrowths that we have here. And what is also known is that it can happen that we have switches from invasion modes depending on interaction between cells and the cell extracellular matrix environment. So what we were really focusing in this work on that I will present you in this first part is to which extent pressure or pressure changes may also drive the onset of invasion. So we're not looking so much into the question if it is the classical cell migration that drives motion, but we wanted to study what happens about pressure here. And how we did this was actually using light sheet microscopy. And the way we actually prepared our model systems is a classical way of generating spheroids. So you basically start with a 4D AL dwell plates. You have a non-adhesive surface. You add cells. They start about within 3 days forming such spheroids, and that you can pick up. And then, for example, here that is a capillary. You can embed then the spheroids into a capillary, and typically here we use collagen to fix it in there. And we can play with the collagen concentration to have interactions that might be mediated by stiffness or by other factors. You can also do this with other cells, but we here use HeLa mainly because it is one of the oldest systems here. So this would be one of these images that you already saw in the first slide. What you see here are the nuclei that are marked with, so basically the histone H2B with M-cherry. You also see here in the background just some fluorescent particles that we later use for the 3D reconstruction and fusion. It's helpful to actually make this a little bit easier. The nice thing is that we can really visualize this with a light sheet here at a subcellular resolution, and later I will show you then the 3D views that we get out of this. But of course, it's not that the spheroid is just sitting here in, let's say, like an environment that's black. In reality, what we have is the collagen here. This is just marked fluorescently. I will most of the time not show you the collagen. You will only look at the spheroid, but there is always a collagen matrix around. It's just avoided to make the images nicer. Now, what we were doing, actually, we're recording these images, as I said, in the light sheet, and that we could then now nicely reconstitute here these three-dimensional images so that we really have the full view of this spheroid, of this tumor spheroid. And here's an example where we actually put these in a 2.5 milligram per milliliter collagen situation. You can already appreciate here that even so I call it spheroid, because typically we look from the top, in reality it's more like an oblate. It was more like a flat situation. That depends a little bit on the cell type. Sometimes you see more of this, sometimes really round objects. Now, you can now take time lapses of this. So we just take typically every 15 minutes, a full 3D scan of these systems, and then you can see how actually here the cells migrate. And this is over 12 hours. And as you can see, these HeLa cells, they don't really invade. There seems to be no special things going on. So we don't see any invasion into this higher collagen density situation. And if you know the field, you might know that actually in a typical situation, people say that if you have a higher stiffness of the environment, then cells start to move out more. So we actually also thought we should maybe play a little bit with the collagen density. In our hands, it actually turned out when we increased the collagen concentration, so making the environment stiffer, we didn't see any change. But then we also went to softer environments just to take a look what's going on there. And that's what you will see in the next movie. So when I start the movie, just recall it's exactly the same situation as before, same cells, same preparation. The only difference is now that we have 5 times less collagen. So we reduce the collagen concentration to 0.5 milligram per milliliter. Now, if we take a look at what happens now, the effect is drastic because it's the same time scale, everything is the same as before, but we kind of see almost an explosion-like change here in the system. We see these bursts of cells that start to move into this low collagen concentration. And that was, of course, kind of like mind-blowing to us because we really wanted to understand what the hell is going on here, that these cells start to move outwards. Also, literature tells us that they shouldn't because the stiffness here is going down, it's getting softer. So just to kind of like look at this side by side, on the left, we have this explosion, these bursts like, right, on the 0.5 milligram, and here on the right, we just have 2.5. Same cells, everything is the same. The only difference is that here we have more collagen. So what the heck is going on here? You can quantify that, of course. You can look, for example, here, how many of them have exploded after a certain amount of time. You can see very nicely that almost here in this case, all of the time we saw that there are bursts in the low collagen concentration and no bursts in the high collagen concentration. You can also track the cells now, actually. Here you would see like these little balls that would be a cell. So we can get access now to the single cell migration path. And as physicists, we now started to try to understand a little bit better what's going on by looking or appreciating actually these trajectories. Now, the question really comes to like, how do the cells now move within these two different phenotypes? Again, same cells, everything is the same. We didn't change anything on the cell, only the environment. The first thing we looked at was actually trying to understand their migration pattern by using mean square displacements. If you don't know about it, it's a very nice way where you can differentiate between purely random motion. Purely random motion here would have so-called power law exponent of 1. You will see that later in the line. We can have directed motion, right? That's a super diffusive situation. That would be an upward curved situation here. And we can have constrained motion. That means the cells cannot escape a certain situation. And that's something you can very nicely analyze with this mean square displacement. Now, if we look at the data here, this is the mean square displacement with delay times, and you can fit this here with such a classic